for this journal club, we're very excited to have Łukasz Kidziński presenting his recent paper on deep neural networks enable quantitative movement analysis using single camera videos. And Łukasz has been very helpful with AIMI. He helped plan the researchathon that we had in June. So he's familiar with AIMI, and we would like to get more familiar with his work. But Łukasz is currently a research associate in the neuromuscular biomechanics lab at Stanford, applying computer vision and reinforcement learning algorithms for broadening understanding of human movements and performance. Previously, Łukasz was at EPFL in Switzerland, where he was developing methods for measuring and improving engagement of users in massive online open courses. He obtained his PhD at the University Libre de Brussels in mathematical statistics, working on frequency domain methods for time series of functional data. So we're very excited to have you, Łukasz, and we're excited to learn more about your paper, which just got published in Nature Communications. So congratulations, and looking forward to your presentation.
Thank you very much for the introduction and the invitation. So let me jump right away into my work. So that's a joint work with Brian Young, a master's student at Stanford, who was working in our lab for a little bit. Jennifer Hicks, Apurva, Ray Gopal, Scott Dolb, and Michael Schwartz from University of Minnesota and Gillette Children's Hospital. So one of the main objectives of our lab is to analyze human movement and human gait. I'm in the neuromuscular biomechanics lab, and the way we analyze this movement is through running various simulations and analysis of movement of children, young adults, older adults, and basically any demographics. So why do we analyze gait? Why we are interested in that? The first motivation for analyzing gait is coming from neurological disorders. So many or most of the neurological disorders, such as Parkinson's disease and Alzheimer's disease, normally cause some form of impairment of movement. And that's normally for patients, that's a problem on its own, that patients just lose their mobility and just cannot achieve those tasks, the everyday tasks that they were normally used to. But also there are some social problems with that, like when your gait doesn't look completely normal, then you lose your confidence, you're less active, you don't go visit your friends and so on. So there are many layers and many implications of impaired mobility. Another target population that we deal with is children's population. Here also neurological disorders are limiting their function. So disease like cerebral palsy affects around 0.1% of children in the US and worldwide. And it's a neurological disorder that causes overstimulation of muscles. Those muscles cause bones to grow abnormally. And in the end, children often end up in a wheelchair. So we basically want to help them. And I will tell you in a second how we want to approach that. And the other population is population of prosthetic amputees and prosthetic patients, where we want to analyze gait of subjects so that we can build better devices, either for prosthetics or also assistive devices for making them walking better and faster in different scenarios. So just to give you a more concrete example, let me show you a short video of a patient with cerebral palsy. Yeah, as you can see here, I see it on my other screen that is kind of low frames per second display, but the problems that those children have is that, as I was saying, the bones are growing abnormally, and they tend to have stiff muscles. They land on their toes. They don't have normal gait as we are used to. So the interventions that normally situations are surgeries and some assistive devices for them to walk. But again, the limited function can cause them to be less active and then socially limited. So how do we help these children? So normally when we want to prescribe some treatment, they first visit a physician, and then a physician prescribes a visit in a gate lab. A gate lab is a room like this, filled with cameras all over the place. So those cameras are like $100,000 worth equipment. There's a technician who operates those cameras. There's a physical therapist who puts markers, those small white dots, on the body of the subject. Those cameras are registering positions of markers. And from those recordings of high frequency expensive cameras, we can derive trajectories of those markers. Then a technician tries to fit a 3D model of a person to those markers. And based on that, we read kinematics, so joint angles of the child. And based on those kinematics, comparing them to different children, we can take some decisions. So when we see that they bend their knees too much, we may want to lengthen their hamstrings, for example. So there are some changes in kinematics reflect, surgeries that we choose are based on those joint angles that we collect, plus some other variables like interviews with parents, interview with the subject, and so on. And that's all great. The problem with this approach is that it's extremely expensive. So it's very expensive. So the cost of a visit is at around $2,000 per visit, because many people are involved, and that's normally not where the hospital makes money. So that's a cost that they would actually want to avoid. And if they were able to just prescribe their perfect treatment right away, that they would prefer to do that. But that's not possible. So like they really need to do that. And it's not only expensive, but also only some hospitals can afford that. So not every hospital has a gate lab. Not every children's hospital has a gate lab. So that's also available only for a limited population. And then, of course, in the countries with limited healthcare, it's much worse than here in the US. So we've been thinking in the lab how we can streamline this process. And one approach is to use some cheaper sensors. And there are those inertial measurement units that you have in your mobile phones that could be used here. And there are technologies where you put those IMUs on the body of the subject, and you measure. So it's an accelerometer, gyroscope, sorry, like it's gyroscope and accelerometer and magnetometer. And based on those three signals, we can derive position of the sensor, and then based on those positions of the sensors in 3D, we can derive again joint angles. So that's a cheaper alternative, but again, you would need a physical therapist to put those on the subject, and it's still quite cumbersome. So we were thinking if there is a possibility to achieve similar precision as we get with those optical motion capture systems, like the one you can see here, but using just a single camera. So in the ideal scenario, you can imagine that we just take out a camera from our pocket, we record the child, and based on this recording, we prescribe a treatment. And that's, in theory, this could work, because when you talk with the physicians in this space, it turns out that they based on the video recording of a child, they kind of get already enough information to prescribe treatment quite well. So maybe there's already enough information in the video. Now, the problem with the single camera video was that until recently, it was really difficult to build algorithms for detecting, for extracting information from unstructured videos, because of the different backgrounds and the different lighting conditions and many other variables that are influencing the scene and then how the video is recorded. So it was just very expensive to build an algorithm for that. But thanks to the deep learning revolution, hopefully we can approach that differently. So now I will. So just to wrap up the current workflow, right now it's completely based on those expensive cameras. We take measurements and we record those markers in 3D. We take anthropomorphic measurements of the subject, we then need to process the data and get the report. So that's an expensive workflow. Now the hope is that we can replace that with machine learning and computer vision. And the basic idea is to just replace the marker collection, the extraction of those positions of markers with a computer vision algorithm that gives us those positions, maybe not as robust and not as precise as the optical motion capture, but good enough for generating this report at the very end. Here I have two brief slides on the actual method from computer vision that we're using. So we are using convolutional neural networks that I suppose many of us here are familiar with. But just to bring back the idea, is the very basic idea is that we take an image, we run a certain filter, and this filter detects certain features in the image. So by running a filter, I mean that we take those 9 pixels from the image here, we multiply those pixels with this matrix, and we get one number for all those 9 pixels. And if we convolute the entire image with a filter like this, it will turn out that the response that we'll get looks like this. So you can see that the filter that I presented here can act as a edge detector. At least some edges are detected here. And now the idea is that if we use a data-driven approach for choosing parameters of those filters, we may find other features that we are interested in. In particular, for the test that I was just describing, we would like to find ankles, knees, hips, and the other anatomical points in the body. So for that, we'll only need some metric for evaluating if the filter is good. So for that, we have a bunch of metrics that we can use, but like just one example is to measure if the point that we detected is close to the point that was pre-annotated by another person. So that would be the basis of our data-driven method, that we basically have tons of images where we annotate anatomical points, and then we choose filters in such a way that they give predictions as close to the points that were annotated as possible. So we can come up with some Gaussian-like metrics for the distance from the point that we are interested in, and backpropagate those differences to get as good filter as possible here for finding the actual eyes and other landmarks. And of course, we need a large data set with annotated images. And here, the main basis for algorithms that we are using is the COCO data set with 200,000 images, 250,000 person instances annotated, 1.7 million key points of people annotated, where by key point, I mean those anatomical landmarks. And with this annotated data set and the metric that I showed and the approach of optimizing the filters, we can actually build a neural network that would predict those points very accurately. And the algorithm that we use in the paper is OpenPose. So the OpenPose algorithm solves one more problem in this context. So now I was explaining to you how we can detect key points, so those anatomical landmarks. Now the problem is that if you have two people, you sometimes don't know how to match certain points with each other. So we don't know if from this shoulder, the arm goes in this direction or if it goes up. And the cool trick that they used in OpenPose was to annotate, to also, from those annotations that we have, also derive the so-called part affinity fields, where they, for each point, they can estimate the direction from, in this case, from shoulder to elbow. So if we are close to the shoulder and the elbow is here, we know the ground truth that the true elbow is here and the true shoulder is here. So for all points here, we can get this affinity field, the same here. And now when we have those two predictions, we can connect the dots by using some graph algorithms for finding optimal graphs under certain conditions. So that's the basis for what we are doing in our paper. And now the entire workflow that we have can be replaced with following, where we basically just take a video camera recording of a subject. We run this key point detection algorithm that I've just described. From that, we get trajectories of body landmarks. In our paper, we are interested mainly in landmarks related to lower extremities. So we are interested in toes, ankles, knees, and hips. We'll look at those trajectories. We feed those trajectories into a convolutional neural network again. And now we want to predict, based on those trajectories, we want to predict certain metrics from a report and that was generated in some other way. So in this case, as I'll show on the next slide that what kind of variables we're predicting, but those are variables that we got from the hospital we are working with. So the advantage of this framework is that it's fundamentally cheaper than the optical motion capture that I showed before, because you just need a mobile phone, you need some compute for inference in those neural networks, and that's it. So like in most cases, we would actually be able to run it even on the mobile phone. And then if you have access to the cloud, it will be a very cheap processing. So now the question is how well that can perform. So can we actually predict gait metrics using those 2D videos that we have collected with a mobile phone? Can we predict changes over time? So ideally, we would like to, the ideal use case for this technology is, for example, where we perform a surgery on a subject and we want them to monitor their movement after surgery, so that we know if the surgery worked, but also we know if if the subject should go back to the lab and or to the hospital to get another surgery. And then another use case that we could imagine is predicting if a subject needs a surgery or not. So we would like to allow parents, for example, in remote locations where they don't have an access to a gait lab, to just run these algorithms and predict if a subject needs a surgery or not. So the data set that we had was a data set from Gillette Children's Specialty Healthcare, where they got 1,800 videos collected over the last 30 years. The videos were fairly controlled, as I will show you examples in a second. We had over 1,000 subjects, and we had access to optical motion capture data. So optical motion capture was collected in a separate trial, but during the same visit. So the subject first was walking in the room without those reflective markers, and the video was recorded. And then they put those markers on the subject and they asked the subject to walk again. So we cannot match perfectly those two modalities, but the high-level metrics from motion capture that we're interested in can be used as ground truth for our algorithms for predictions from videos. So let me show some examples here. So here is one video from the hospital where we already applied open pose algorithm. As you can see, the open pose algorithm performs quite well. So there's some noise and there are some problems. There are people in the background, but since we have so many videos, we managed to choose videos where open pose performed well. And then with some extra post-processing, it actually seemed to be sufficient for our downstream analysis. Yeah, so that's how it looks like. So now how did we train those networks? First, the ground truth that I was referring for action and reflect of the subject. So yeah, basically the angle in the knee at the maximum knee angle during walking of the subject. It's called minimum because of how it's actually measured as an angle between the basically the minimum angle is the closest you get to the maximum extension. We were interested in predicting walking speed, cadence, and gait deviation index. So gait deviation index is an index, a holistic measure of how abnormal is the gait of the subject. It comes from the cerebral palsy literature, and it's one of the most popular metrics of gait impairment on the scale from 0 to around 100. So 100 is a normal child, between 190 and 110 it's normal, and then any deviation outside of that is considered as impairment. And the more deviation you have, the more the worse is the impairment. And the other metric that we're interested in is the surgery likelihood of getting a surgery. So I'll talk about that later. Now for training, as I was explaining, we have those trajectories of markers. So this gives us a multi-dimensional time series. We feed it into a neural network, and we have this ground truth to backpropagate, and we get optimal weights of the network for those predictions. So now how does that perform? We first compared that to raw predictions from OpenPose. So as you can imagine, from OpenPose directly, we can calculate some of those metrics. So for example, knee flexion, we can just assume that this projected angles are our ground truth, and we try to, we can assume that those projected angles are good enough for predicting ground truth, and we can simply see if the peak, in this projected angle from OpenPose is a good predictor of the true peak knee angle that we get from optical motion capture. And with this very basic method, we get prediction at with correlation 0.51 on the test set, while with a neural network that takes the entire lower extremity and the time series into account, we get a correlation of 0.83. For the gait deviation index, we got correlation 0.75, and that was close already to the stride-to-stride variability in gait deviation index that was reported in other studies. So given that our metric is computed at the entire on the entire trajectory on the entire trial, we can capture some of the gait deviation variability that we would like to. So we're kind of expecting that here we are approaching the upper bound of what can be possible in this setting. Now, there are ways to improve our network. So throughout this work, we've been working with sagittal plane, so the side view, but it's kind of clear for practitioners here that there is some signal in the frontal plane too. So what we're trying to see is if the mean foot progression angle, the question that we had was if there is some information in the frontal plane that could improve our predictive models. So yeah, like we are just interested in what didn't we capture with our technique. And we had access to frontal plane 2 for some, we had it for all subjects, but the problem was that it's, after several steps, only a very small part of the subject is visible, and OpenPose was failing a bit. So we just use that more for validation rather than for improving our results. And we saw that if we take residuals of our model and we correlate it with the foot progression, which is basically the ankle in the ankle going on the side that so it's kind of a rotation around the y-axis. If you consider the y-axis as the vertical line from the ground upwards. So if this angle, so this angle is not, or like rotation in this plane is not really visible from the sagittal plane. So we're expecting that maybe there is some extra information here. And indeed, when we correlated the residuals of the GDI model, we saw that there is some extra information here. Now, other variables that we were interested in is change in knee flexion at maximum extension. So we were interested if we can really use this tool for tracking patients longitudinally. So we were interested if we take measurement today at the clinic and we take videos today, is the change from today to next week, where next week the subject is measuring themselves only using the camera at home, is this change reliable? So, and for that we were looking at all pairs of visits where we have visit at the time point t and the visit at the time point t+1, and we wanted to predict the change in the knee flexion parameter, and we see that again we get 0.83 correlation, slightly more than previously actually. So that makes it reliable for these longitudinal studies. And the next model that we had was for predicting the likelihood of getting a surgery. And here again, the CNN model predicted the surgery a little bit better than basic model based on just the GDI metric. So here, by the surgery event, I mean the not only the prescription of the surgery, but we were predicting if the patient actually got a surgery after the current visit. So we have a video of the current visit, we have the optical motion capture, and we were trying to use those models for those signals for predicting was there a surgery event after the current visit. And that's again promising. It shows that we capture some information. It's really hard to perfectly predict those variables, as there's a lot of factors coming into play when you are deciding on a surgery. So what are the key takeaways from this work? First, we showed that that those techniques already are at the point that they can be used in practice for that they can be used at least for research in cerebral palsy for analysis of gait. We saw that we approach we approach accuracies close to the upper bound of what we can actually get in this context. So yeah, we're very happy with these promising results. However, of course, those tools were built on the videos collected in the clinic. So there's still a lot to be done to validate if that can be really used as a clinical tool used outside of the clinic. That still remains unclear. One big takeaway is that clearly we were showing here for cerebral palsy, but exactly the same framework can be applied to any other scenario. And now we are actually trying to build some tools for osteoarthritis and for analyzing gait of subjects at scale. And the big value here actually comes, especially in these hard times of COVID, where it stopped and limited a lot of biomechanics research and human movement research, or any other human subject research, clinical trials, and so on. So we hope that by releasing tools that allow people to run experiments without access to the lab, we can, first promote our current methods, but we can really contribute a lot into biomechanics research, because not only now with those COVID limitations, you can still run experiments, but also your experiments are run at scale. So you can invite subjects not only from Silicon Valley, but also subjects from all over the world. So our short-term vision is to just release those tools that we have. And then the long-term vision is to really build a platform for biomechanics researchers and later also for clinicians to collect the data and analyze the data at scale and at high frequency, even if we get slightly less precise signals from mobile devices, maybe we can still get a lot of value if we collect data and in the environment at home. So that's I prepared some other slides, but I think I've been talking a lot already, so it will be great to switch to more conversational mode and answer questions and talk and discuss benefits of these methods.
Thank you, Lucas, for that very nice overview and a very nice presentation of your work.